Swayam Prabha. Digital India. Educated India.
Okay, so now we will go on to another topic on eigenvalues and eigenvectors. So what we did was, we have seen the combination of columns of A that is closest to B. So we are going to see, just consider, we said that a matrix represents a linear transformation, and we are going to assume only square matrices, which means you are taking vectors from one dimensional, from say n dimensional space and transforming into vectors in n dimensional space. So let's take the simple example which transforms two dimensional vectors into two dimensional vectors, and then ask this question, what does it do? So what happens to the, we know what it does to the vector 0, 1, right? Or you know what it does to the vector 1, 0. You get the vector 1, 1. You know what it does to the vector 0, 1, you get the vector minus 2, 4. So this is what happens in the original space, and this is what happens in the after transforming. 1, 0 becomes 1, 1. Likewise, 0, 1 becomes minus 2, 4. So now the vector 1, 1, that is a 45-degree line. What happens to it after transformation? You get 1 plus 1 minus now the vector minus 2, 1 after transformation. What about this vector? What happens to this vector after transformation? You end up getting, let me see. So you get into minus 2, 1. So this is right. So you started with a vector minus 2, 1, and you ended up getting a vector minus 4, 2. Right. So you started with this vector, and you end up getting a vector minus 4, 2, which was again, you get this vector after transformation, minus 4, 2. Now, can you notice some particular difference what is happening to all, one property which is shared by one vector, but it is not shared by the other three vectors. All of these three vectors, after transformation, they are getting rotated. This vector is not getting rotated. It has changed in length, but it has not got rotated. So therefore, for this matrix, this seems to be some kind of a preferred vector because it resists rotation. It is not getting rotated by this matrix. Whereas many of the other vectors that we saw, they were getting rotated by this matrix. Whereas this particular vector over here, it was somehow immune from being rotated. It changed in length, but it was immune from rotation. So such a vector is called an eigenvector, which is one example of a vector which has this property. This is a very trivial solution which we will not be interested in, a zero vector. Right? You take the zero vector, any matrix on action on zero vector, you will get a zero vector. But that's not very interesting at all. Right? So we will assume that we are interested only in non-zero vectors when we are asking for this property. That's why I am asking for this property. I want a non-zero vector, a non-trivial vector, such that Ax is a vector after transformation. If it has to be, if it continues to share the same direction as x, what does it mean? Ax and x should be collinear with each other, which means they should be related by this equation over here, Ax equal to lambda x, where lambda is an unknown scalar. In this case, what was the value of lambda? This was minus 2, 1. Right? X was minus 2, 1. Ax is equal to 2 times minus 2, 1. The length of the vector changed by 2 units, by 2 times. It did not get rotated. And when I say, okay, that will come to that later. So Ax is collinear with x. So Ax and x, if I want to ask this question, are there such vectors? I am interested in searching for vectors such that Ax and x are collinear with each other. So Ax should be equal to lambda x. So let me go back here and then equal to lambda x. I am going to write this as lambda times I times x. And I will bring everything to the left hand side. Ax minus lambda I times x equal to 0. And now I can do this. And recall we talked about the solutions of a matrix Ax equal to 0. Here I am not about Ax equal to 0, I am only interested in A minus lambda I. And what was it? This always has a solution, the 0 solution, but we agreed that we do not want the 0 vector over here. We are only interested in non-zero vectors which do not get rotated, so that Ax is equal to lambda x. And after a few algebraic simplifications, we got that A minus lambda I times x should be equal to 0. Lambda is yet unknown. X is also unknown, lambda is also unknown, but we want non-zero, non-trivial solutions to this. By that I mean x should not be equal to 0. So what does it mean about this? If I want non-trivial, non-zero solutions to a system of equations where the right hand side is 0, that can happen only when the determinant of this matrix is 0. So I can get determinant of A minus lambda I equal to 0. So for this matrix over here, if in this case I gave you one of the eigenvalues and the eigenvectors. So that value of lambda which satisfies this, okay, let us come back. The value of x which satisfies this condition is called an eigenvector. Lambda is an eigenvalue. Now both of them are still undetermined as yet. The one way to find out the first we can write the eigenvalues is to get a system of nonlinear equations called, say, determinant of lambda I equal to 0 will give you the eigenvalues. And then we can find the eigenvectors. So for this particular matrix, we know one of the eigenvalues was lambda equal to 2. Now you can expand this out, we won't do it here. You will get a quadratic equation in lambda. If it were a matrix of size 3 cross 3, you would have got a cubic equation. So matrices of size n cross n, you will get a polynomial equation of degree n. Therefore, under some condition, okay, so in this case, one of the equations you expand this out for this particular matrix, you get lambda equal to 2, and the other value of lambda would be 3 in this case. I have not found, and one of the eigenvalues was minus 2 comma 1. This was the eigenvector corresponding to lambda equal to 2. Another eigenvalue is lambda equal to 3. So we can now come up with what is the eigenvector corresponding to lambda equal to 3. How do we do that? We just say Ax is equal to 3x, right? And then say 1 minus 2, 1, 4, and this is x1, x2 equal to 3x1, 3x2. So you expand it out, you get x1 minus 2x2 is equal to 3x1. So 2x2 equal to 2x1, that is the first equation. What happens to the second equation? You get x1 plus 4x2 equal to 3x2. So you get the first equation was minus 2x2 equal to 2x1. So both of these are the same set of equations, x1 equal to minus x2. And that is not surprising, right? You do not really have two independent equations, you have only one independent equation. Because there is a non-trivial solution, which means the columns of A are dependent on each other. So obviously you will end up getting infinite solutions. So any vector which satisfies where the first component is negative of the second component is an eigenvector for corresponding to second eigenvalue 3. So the second eigenvector is 1 minus 1 and the corresponding eigenvalue is 3. The first for corresponding to the eigenvalue lambda equal to 2, the eigenvector is minus 2 comma 1. Now it is not that this is the only eigenvector. Any vector which is a multiple of this is also an eigenvector. Likewise, any vector which is a multiple of 1 comma 1 minus 1 is also an eigenvector. But corresponding, they are all going to be just collinear with the vector either minus 2 comma 1 and 1 comma minus 1. And the eigenvalues are lambda equal to 2 and lambda equal to 3. So what we have now done is, for this particular matrix A, there are two preferred directions, and the directions are -2, 1 and 1, -1. And these are the eigenvectors, and these are the corresponding eigenvalues corresponding to these eigenvectors. Okay, so what we can also do is, let me so I have over here, let me call the eigenvectors V1 equal to -2, 1. The second eigenvector V2 was equal to 1, -1. It could have been -1, 1, any vector which is parallel to 1, -1. So I am going to write this A V1 equal to 2 times V1, we know that, right. Likewise, A V2 equal to 3 times V2. So I am going to write a vector V or S as consisting of the eigenvectors V1, V2, and a vector capital lambda which has 2 and 3 on the diagonals. It is a diagonal matrix which is written over. So what I can write, I can combine all of these as a vector of equations AS equal to S. Right. If this is not clear, we will just AS equal to this, and this is equal to lambda times S. AS is equal to lambda S, and in this case you will notice that the two eigenvectors are independent, therefore they can be, this matrix S is invertible, A equal to, yes. I am sorry, I think we need to fix this somehow. AS is equal to S lambda. Lambda is a vector of the diagonal matrix consisting of the eigenvalues in the diagonal, and A equal to S lambda S inverse. Now, why is this this kind of a representation is useful? You will also see in the in the tutorials. The advantage is that if I want to take arbitrary exponents of the matrix A, what is A square? In A square, we know how to do this multiplication and get that, but I can give you now a very simple representation in terms of A square is A is S lambda S inverse, S inverse right. Now S inverse S is identity, so this is just S into lambda square S inverse. What is lambda square? Is a diagonal matrix, therefore the entries on the diagonal also get squared. Likewise, I can do the same thing for A cube, and for an arbitrary exponent, so when you can have this kind of a representation, when you are able to write A equal to S lambda S inverse, A power n is very easy to compute. It is just S lambda power n into S minus 1. Now in order to be able to do this, there are a couple of things which I glossed over. The first thing is, how were we guaranteed that we could solve the system of equations to get the eigenvalues? Because it was a nonlinear equation. How do you know the solutions always exist? Now, it's a nonlinear equation, it's a polynomial equation. It may not have solutions in the real numbers, because it's a nonlinear, it could end up getting complex numbers as solutions. So even though the original matrix consisted only of real numbers, because of the polynomial equation that you wrote, the eigenvalues could become complex. That is one problem which I did not address that, about the existence of the eigenvalues. As long as you are ready to work with complex numbers, even though the original matrix consisted of real numbers, the eigenvalues can always be found. You can always find n eigenvalues because it's a complex, it's an algebraic equation, a polynomial equation of nth degree, and if you are ready to work with complex numbers, you will always be able to find n complex roots for that, but n roots, some of them may be complex for that particular polynomial equation of degree n. For most of the problems that we will be looking, for most of the applications that we will be looking at in this course, and later on, especially in data, when you work with certain kinds of matrices, especially symmetric matrices, the good news is that for symmetric matrices, the eigenvalues are always real. You will not have to worry about complex eigenvalues entering, even though the original matrix was a real matrix. If the matrix is symmetric, the symmetric matrix is when the matrix is equal to its transpose, all the eigenvalues are real. So you don't have to worry about complex eigenvalues entering. The second problem that can occur is you may end up having real eigenvalues. That's possible. It may or may not be a complex symmetric matrix, but you may end up with a matrix having eigenvalues real. But how do you ensure that the eigenvectors are all independent? It is possible that you may not be able to find the eigenvectors which are all independent of each other, corresponding to different eigenvalues. In this case, the two eigenvectors -2, 1 and 1, -1 were independent. Now, good two factoids, eigenvectors corresponding to distinct eigenvalues are always independent. So this was corresponding to lambda equal to 2, this was corresponding to lambda equal to 3. Eigenvectors corresponding to distinct eigenvectors are always independent. But what happens when eigenvalues are repeated? When eigenvalues are repeated, there is something called, certain matrices are called defective matrices, which means they do not have, certain eigenvalues are repeated, but you may not be able to find enough independent eigenvectors, in which case you will not be able to do this business of inversion over there. So there is some other, you can not reduce it to this form, you can reduce it to what's called, you cannot reduce, the lambda will not be a diagonal matrix, but it will be a block diagonal matrix, and you can get what's called a Jordan block form. However, we will, as I said, for several applications that we will come across when we are handling data, our matrices are usually symmetric, which means there are two things which are when they're symmetric, eigenvalues are always real. More importantly, you can find independent eigenvectors. I am not saying all the eigenvectors are perpendicular, I am saying you can find enough independent eigenvectors, and not just independent eigenvectors, the eigenvectors will be perpendicular to each other. So what that means is can be written as not just S lambda S inverse. In the case of a symmetric matrix, it can be written as Q lambda Q transpose. Because the eigenvectors are all perpendicular to each other, you can show that in the case of a symmetric matrix, eigenvalues are all real symmetric matrix, eigenvalues are all real, all the eigenvectors you can find enough independent and perpendicular eigenvectors. And that will be useful when we look at some problems in optimization and when handling data. It will be useful to be able to write things in terms of perpendicular eigenvectors. Okay, so just we will recap what we have learned so far. Eigenvectors are those non-trivial eigenvectors which satisfy Ax equal to lambda x. Non-trivial meaning x should not be equal to 0, because otherwise, remember why did we insist on x not equal to 0? If x were equal to 0, then any value of lambda will satisfy this equation. Right? Then doesn't make sense to be asking this question at all. We want non-trivial, very interesting solutions, interesting vectors which are immune to rotation. So Ax should be equal to lambda x, and you bring everything to the left hand side, you can show that the lambda is called an eigenvalue, x is called an eigenvector. You can get the eigenvalues by solving a polynomial equation of degree n, which is determinant of A minus lambda equal to 0. And when the eigenvectors are independent, you can write it in this form: A equal to S lambda S inverse, where S consists of the matrix of eigenvectors. Lambda is a diagonal matrix having eigenvalues on the diagonal. Other couple of interesting things about eigenvalues and eigenvectors. Trace of the matrix A is equal to sigma of lambda I. This we can show from by looking at this so-called this is also called as the characteristic equation. So trace of the matrix is equal to sum of the eigenvalues, and product of the eigenvalues is equal to determinant of A. Okay, so now before we finish this, I just one point which also I have to mention. I said an eigenvector cannot be the zero eigenvector, but an eigenvalue can be zero. There's nothing which prevents an eigenvalue from being zero. Right? Any vector, suppose x has linearly dependent columns, then obviously you can find non-trivial solutions to Ax equal to 0, right? 0 times x. If the matrix A has dependent columns, in which case lambda is equal to 0. It's perfectly valid to have lambda equal to 0. It is absolutely incorrect to have 0 as an eigenvector, but it's perfectly valid to have 0 as eigenvalues. So for a singular matrix with determinant equal to 0, one of the eigenvalues will be definitely equal to 0, which is also obvious from over here. Because for a singular matrix, determinant is equal to 0, it is equal to product of the eigenvalues, therefore at least one of the eigenvalues has to be equal to 0 for a singular matrix. Secondly, for even though the original matrix may be real, you may end up with complex eigenvalues. However, if the matrix is real and symmetric, all eigenvalues are real, and you can find linearly independent eigenvectors. Not only are they linearly independent, you can also find them to be perpendicular to each other. And one advantage of studying this eigenvalues and eigenvectors is, I have mentioned it briefly over here, certain times instead of having to take any arbitrary basis or standard basis, by writing vectors in terms of the eigenvectors, because if eigenvectors form a basis, any other vector can be written as linear combination of these vectors. Therefore, certain times analysis or certain intuitions or insight may become obvious when you write it in terms of this, and we will see an example of that in the next, maybe in the next when we talk about optimization and quadratic functions. We will see how that intuition is useful in the ability to write vectors in terms of eigenvectors.